A digital twin for a power electronic application means the virtual digital model of this system. If you use a hardware-in-the-loop setup as a digital twin, then this means that the virtual system is only a partial model of the power electronic topology and controller. Therefore, we have two different approaches. One is the so-called controller hardware-in-the-loop approach, where we have only the controller physically available, and the power electronics topology and its components are emulated by the real-time system. The other approach is the power hardware-in-the-loop setup, where we have the full topology and the power electronics components available, and the controller is emulated by the real-time system. The first thing is that a digital twin enables faster development cycles, or in other words, the acceleration of the development process. This means that we can develop control schemes, control algorithms, without having the full prototype available. We can start hardware development and software development at the same time, and this speeds up the whole process. Another thing is that we have a risk reduction during the development and testing phase. Because with the hardware-in-the-loop setup, there are no dangerous or hazardous voltages and currents which are applied in the prototype. And so also the testing process is really safe compared to the laboratory tests or field tests. The challenges for digital twins based on hardware-in-the-loop setups are that in principle these systems would enable a completely automatic test sequence. So there is no need of an engineer sitting behind a computer and controlling the whole testing process. But this fully automatic testing environment has to be developed, which is part of the PowerizeD project. Regarding the limitations of hardware-in-the-loop systems, we will see this especially in context with the integration of wide bandgap semiconductors, like silicon carbide or gallium nitride. Here we have prototypes with increased switching frequency, and if you here, for instance, use a controller hardware-in-the-loop setup, also the sample rates has to be increased for the simulation of the wide bandgap semiconductors. And this is a real challenge for the real-time system to achieve such high bandwidth. So the major advantage of a hardware-in-the-loop setup is the scalability and the versatile approach, which means we can set the electrical parameters from low voltages to high voltages, to high currents to low currents, and use in principle low or high power systems at the same time. Especially for high power setups, the hardware-in-the-loop system shows an advantage because of minimizing the risk during the testing process. So nowadays the hardware-in-the-loop setups are mandatory during the development process of power electronic systems, because the development and implementation and testing can be done without having the real hardware present at the implementation and development process. On the other hand, the testing of different scenarios under extreme conditions is also possible, which might be not that easy on a real system. Especially for high power applications, the hardware-in-the-loop setup or the digital twin based on a hardware-in-the-loop setup shows its strengths. So in past we've used the hardware-in-the-loop approach for 1 megawatt battery energy storage system, where the battery energy storage system was installed in the field while we had here at AIT the digital twin available. So in the field, it's very difficult to test every mode and every function of the system, but with the digital twin, it's possible to analyze the whole system and to test the functionalities.